Thank you for the introduction, Luis. Yeah, again, this will be in English. I apologize for that, but I hope you've all got the translation on. So as Luis mentioned, I'll be talking about the geometallurgical design of a large copper moly concentrator. That's a picture of me, but you can see me on the video, hopefully. And there are my details if you would like to contact me afterwards. So the project that I'm going to talk about today is a very interesting project for us. And in fact, many of the tools and the technology that we've developed over the years has been developed together while working on this project. It's a very large copper moly concentrator. It's due to come online next year. So yeah, anyone in Chile would be familiar with this. And there are some of the details of the operation of this circuit. As shown in the slide. How was SGS involved? Well, we got involved in all aspects of the concentrator design. So the comminution circuit, the flotation circuit, both the copper and moly, and the majority of the test work, which was done down in SGS's laboratories in Chile. So this included the geometallurgical tests, SPIs, bondwork indices, MFTs, as well as pilot plant runs and the stage flotation reactor tests that were done. So as I mentioned, this was a very challenging project and we had many problems that we needed to solve along the way. So one of those or of those that came up for the grinding circuit was investigating the different bottlenecks in the circuit. We discovered that we could improve the performance by investigating the bottlenecks, either in the SAG mill, the ball mill, or the process bottlenecks. On the copper side, we needed to select the best flotation circuit. We started with about 25 flotation circuits, and yeah, how do you evaluate which one is best? And so we had to come up with a methodology for that. And then we used that for the production forecasting. And we'll do a sensitivity analysis and show why we chose the circuit that we chose. We'll also get into a little bit of modeling. The stage flotation reactor was a novel device at the time, and so we had to come up with a model for that. And we also weren't able to do the MFT tests on all the samples. So for some of the samples, we only had a standard kinetic test, and so we had to develop a methodology to populate the results for those standard tests where we didn't have a full MFT. And then we also get into details on the moly circuit design. One of the real challenges with designing a moly circuit from flotation test work is having enough sample mass to do test work. You start off with let's say 100 kilograms of copper feed to the copper circuit, and you only end up with 1 or 2 kilograms going to the moly circuit. And that's on the plant scale. Well, imagine in the laboratory where you've got to create a feed to that moly circuit, and now you've got to start doing some test works on that minimal amount of sample. So I'll get into that as we go through. So getting into the comminution circuit design, there's a quick picture of the mill. So doing this, we adopted our standard geomet approach. I've got the 6 steps listed there. So we did a geologically informed selection of a number of samples. Hopefully you were all listening yesterday to Jan and his presentations. He did some excellent presentations there to illustrate how we do that. Once we've selected the samples, we need to do our metallurgical tests on those. Once we've got the metallurgical parameters, we need to distribute them on the block model. We then also need to develop a model of the process plant, and then we simulate those samples through the process plant. And so that distributed set of data and results comes out of our simulator. And then, as I mentioned, we wanted to know the sensitivity of the results. How accurate are these results that are coming out? And can we quantify that accuracy? And that's really one of the niche things that we do here in SGS, is that we're not just giving you an answer, but we're telling you how accurate that answer is. So I'm not going to go into the sample selection. One thing I will show here is a validation that we did a good sample selection after the fact. And so on these 2 graphs, what you can see is a comparison of the samples as tested in red versus the parameters for the SPI and the bond work indices as distributed on the blocks. And you can see that these distributions match fairly closely. So what does that mean? Well, it means that we chose samples that represented the full range of hardnesses on the ore body. And we didn't have a particular bias. So we're not going to get a bias in our overall results. Right, so that's the sample selection. The next step is the metallurgical tests. We have various geometallurgically enabled tests that we do to extract metallurgical parameters. So it's not the plant results, but it's the metallurgical parameters, the ore properties that we will use in our models to simulate the plant results. So we've got we do all these tests based on drill core samples. So they're geometallurgical tests. They tend to only need around 2 kilograms of samples. So you've always got enough material available. So we've got the SPI, the bond work index, and the MFT that you would have heard about already for our flotation kinetic parameter extraction. The nice thing about these tests is they're a standardized test, and so we can compare the results with other typical operations. So here's an example for the SPI, and we have a range of SPI values and different plant databases in our system here. So we can see, is your ore a typical ore? Is it harder? Is it softer? Are we going to need more energy because it's harder to grind? And the same type of database for our bond work index and our MFTs. Right, so once we've got our metallurgical parameters, we need to distribute those on the block model. We do that as Jan would have described yesterday. Essentially, we need to look at the variograms, the correlations in the data, or the hardness numbers with distance. And so if we have 3 samples, as shown here with SPIs, our variogram will determine the weighting of those samples for populating all the blocks in the immediate vicinity. And that allows us to get block values in terms of hardness, SPI, whatever our metallurgical parameters are, distributed over the entire model. And so we end up with something that looks sort of like this, where we've got a distribution of our samples well distributed over the ore body. We've got the various hardnesses measured in terms of the colors, and you can see how those colors have then been distributed onto the blocks through our geostatistical distribution. Right, now we've got our metallurgical parameters. We need to develop a model of our grinding circuit. Felipe went into this in a little bit of detail. So there's our circuit model in this case, a SAG ball mill circuit. And we've got to now run our blocks through this circuit. So here's a little illustration showing roughly what the simulator does. So the block with its properties goes into the simulator, and out will come a tons per hour and a P80. So now we can simulate block by block. We can average that year by year, and we can determine what's the performance of the circuit going to be for our production forecasting. And that's the key part. So let's look at some things that we can do here. So here's a graph which is showing our production forecast for the next 20 years. We've got our tons per hour on the left-hand side axis. We've got our period over here. We've got our target. We're trying to get 4,300 tons per hour here. And we've got our limiting throughput. Now that would be the downstream process limit. So for instance, what's the limitation on the flotation circuit? Right, well now let's do some investigation. Let's run our model. So we get a limiting throughput of our SAG mill. Would look something like this based on the variability in the hardness for each of the years. We've got a limit for our ball mill as well, shown in gray there. As you can see here, the SAG is more limiting than the ball mill. So we're going to get a little bit higher throughput through our ball mill than our SAG mill. And putting these two together with a process limit, we get our best estimate for our production for each of the years. And so this looks fairly good. For the first 8 or so years, we're going to achieve our production. In year 9, our best estimate of our throughput is slightly below our target. And you can see that's mainly because of this SAG mill bottleneck here and hard samples in terms of their SPI values in year 9. But now that we've got this model, we can start playing around with it. We can adjust various parameters and we can see, is there potential to improve the performance of the circuit? So getting into that, first I'm going to show you a little bit about our sensitivity analysis. What we do is we do a Monte Carlo simulation. How this works is that we take our average SPI results for a particular year as an example, and we've got a mean and a standard deviation for that. And so we put a range of SPI values into the simulator together with a range of bondwork indices, and we run these different values. And there's obviously a correlation between those two. But for simplicity, we run these different blocks through the simulator, and out comes a range of tons per hours. Now, this is the range of possible results given the uncertainty in the hardness. And so we can estimate our uncertainty in results. So as an example here, the red line indicates 90% confidence. And so 90% of our results or our simulations or our possible results for that average block for that particular year are above this throughput. Putting this together back on our grind design summary graph, we now have this blue line. So that's our 80% confidence level for our best estimate as shown in red. And we can play around with different parameters. So if we were to try and improve our overall performance, we might want to increase our limiting throughput. Our 5,000 tons per hour has been increased to 5,500 tons per hour. And that gives us a little bit more throughput in most of these years, where some of the samples or some of the blocks were going to be bottlenecked by that process limit. You can see now, even though the SAG mill is still a determining factor on year 9, we now have our best estimate almost exceeding our target. And so we can play around with this and we can vary various parameters. This is going to a 90% confidence. So to be more confident, obviously our results are going to go a little bit less in terms of the 90% confidence on throughput. Okay, now I'm going to get into the flotation circuit. As I mentioned before, a number of challenges on this flotation circuit, not least of which it was these new SFR cells, as you can see there. So I'm going to go into the various parts that we dealt with. The first part was the selection of the flow sheet. How are we going to do this? What flotation circuit is going to give us the best performance? And how do we determine best performance? Is it by grade? Is it by recovery? Is it by the ore being processed? The economics of the project? You know, we could keep building a bigger and bigger circuit and get better performance, but is that going to be worthwhile? Then we can also look at things like the control of the circuit. We don't want to set up a circuit that's inherently unstable and difficult to control. And then we need to look at elements of risk. You know, how is variability going to affect our particular circuit choice? So we went through a number of circuits. We started off with about 25 circuits. We nailed it down to these 2 circuits, which we'll call flowsheet 1 and flowsheet 2. Laguna Seca circuit, named after the Laguna Seca plant in Escondida, and the C+M, which is essentially the same circuit, except you have a mechanical cell operating on the column tail over here. And you'll see why that becomes important as we go through this process. So, as I said, we needed a methodology to do this. And so we came up with this approach, combined optimal grade recovery curves. And there's a nice paper that I published together with my colleague Doug Hatfield a few years ago at the Canadian Minerals Processors. So this takes us through that methodology very briefly. So first thing is to develop a model. Paulo showed us a little earlier how we develop a flotation model. Now, assuming we've got a model and we run our simulator, we may get 2 results like this, with flowsheet 1 and flowsheet 2 giving different simulation criteria or different grades and recoveries. How do we decide which is the best flowsheet? Well, it's hard to decide here because flowsheet 1 is getting a better grade and flowsheet 2 is getting a better recovery. which one do we want? Well, ideally, we want to do an apples to apples comparison. So we want to create a grade recovery curve. That allows us to trade off grade and recovery, and we can see which flow sheet is better at the same grade. So we may get a grade recovery curve that looks something like this. It seems to indicate flow sheet 2 is better. However, we don't know our grade recovery curve. It could look like this, and in which case, again, flow sheet 1 may be better. So again, we've got to make this decision. The reality is, and as shown by Paolo's presentation earlier, is that is just a simulation point, but there's an optimal set of values or simulations sitting further to the right and above, so at higher grade and higher recovery. And so we need to establish what is that grade recovery curve, that optimal curve. And this is an interesting technique that we came up with. Essentially, we developed a tool in IGS called the optimizer. And what it does is it adjusts the operation of the circuit, essentially changing the mass pull in the different flotation units, but doing the corresponding changes in terms of water recovery, different mineral recoveries, etc., when we adjust the mass pull, which we do by adjusting froth recovery. And by doing that, the software and the computer runs through many thousands of scenarios, and it's trying to target the best possible results sitting with the highest grades and recoveries, as shown in this curve here. So we end up with a boundary line sitting something like that. And that's our optimal grade recovery curve that we're looking for. Great, so now we've got our optimal grade recovery curve. Now we can choose informatively which is a better flow sheet. So we can do that for flow sheet 1 in red and flow sheet 2 in blue. And we may get a result like this, and then it's easy. It's easy to say, okay, flow sheet 2 is going to give us better results. Sorry, flow sheet 1 in red is going to give us better results. It's got better grade, better recovery at all points. However, we may get a situation like this, where at high grades, flow sheet 2 seems to get better results, whereas at low grades, when we're trying to improve our recovery, flow sheet 1 is a better option. And so again, we're left with this conundrum. How do we figure out what is the best flow sheet? To add to that complexity, we may end up getting a different optimum for different samples. So sample 1 over here, the blue flow sheet seems to do better, whereas sample 2, the blue flow sheet is doing worse. And again, we've got to figure out a way of combining everything so that we get the optimal result and the best selection of flow sheet for your particular ore. And this is really why a one circuit fits all design is not going to work. And each flotation plant needs a slightly different flotation circuit. So what do we do with 2 different samples? So if we have sample 1 and sample 2 over here, we want to be able to combine them and get the best possible combined weighted curve. And that's what's shown in black here. So what we've done is we've just considered each of these samples equally weighted, and when we combine them with the right points in each, we get this black curve. Interestingly enough, this curve occurs above at 27% copper grade. It occurs at a higher recovery than we were getting for both of those samples. Well, how does that happen? Well, usually you would be selecting equal grades for each sample you process. You'd be setting a target grade for your plant, and you'd be trying to maximize your recovery at that particular target. However, it turns out that you're going to get better performance by maximizing your recovery when you lose very little concentrate grade. And so in this case, we would want to maximize our performance at a lower concentrate grade for the red sample and get a higher grade for the blue sample. Higher grade because we know if we try and improve our recovery, we're going to lose grade very quickly. And so putting these 2 together, we get an optimum sitting over there around about 0.7% extra recovery. All right, so this was just showing 2 curves or 2 samples, but we can run this for an entire set of samples, all of our test work, even possibly our block model, but that allows us to create a combined optimal grade recovery curve. And so we've done that for our different samples, and we've combined them for each of the years of production. So here are some grade recovery curves for the next 10 years life of mine. Again, we can select our target grade. Let's say we're going to select 27% concentrate grade, and then we can see what our overall recovery will be for the different flow sheets for the different years of production. So this is going to help us make our selection. And as you can see, flow sheet 1 and flow sheet 2 are sitting on top here, the red and blue ones, as shown before. Most of the time, flow sheet 2 is sitting above flow sheet 1, getting higher recoveries. And again, we can adopt this approach, and we can continue through the life of mine. So this is the next 60, 70 years of production. Now we've made a decision on which flow sheet. Well, we need to analyze the risk. Did we choose a good flow sheet, but it may be unstable, it may have high risk, and so we need to investigate that. So it turned out that flow sheet 1, the Laguna Seca circuit, is a well-known, tried and tested flow sheet. And so, we were happy to go ahead with that. However, this C+M flow sheet was getting better performance. It was a novel and perhaps risky choice. As we know, in the mining community, we don't like to adopt these new ideas when we're not certain of them. So we had to do a review, and that's where we do a Monte Carlo analysis. So again, like I described before, we set up a range of sensitivity in terms of our average samples going through the flotation plant, and we can see what the sensitivity, how that sensitivity affects the flotation performance. So here we've got two examples. We've got we've got the two flow sheets, flow sheet 1 and flow sheet 2 again, and we've got various samples. To make it simple, I'm just looking at 3 different samples. What you'll see here for sample number 3 in flow sheet 1, it was getting significantly lower results. We've got some recoveries around about the 60, 65%. Very high grade. Turns out this is our supergene ore, and yeah, it can get us very high grades, but it had a lot of copper in it, and so this column circuit just didn't have the capacity to get that flotation concentrate out, and we would lose recovery with that circuit without this increased capacity in our column tail cleaner. So that's just looking at 3 samples. Obviously, we had to combine this over all the ore that we're expecting to be processing, and so we get results that look something like this, where I've put in the sort of 90% confidence lines. These indicate that 90% of the time we're going to get our result for our average sample, or our average ore process for the year, above these lines. And again, you can see that flow sheet 2, not only was it getting better overall performance, but it was getting less sensitivity, less downside risk, and a lower standard deviation. So originally, it seemed like a risky choice, but in the end, it was a far safer choice, mainly because it could mitigate that risk when you have a high amount of copper in your ore. Okay, other challenges, I'm not going to go into these in much detail. The SFR model, I'll go into that a little bit in our Mali circuit modeling. And then another thing was we couldn't do MFTs on all the samples. We had over 1,000 samples tested, and the MFT test is a very robust test with a lot of analysis, and so it wasn't done on all of these samples, and so we needed to populate the MFT results on the samples we only had standard kinetic tests on. Sandy will talk about this tomorrow. It's a novel machine learning approach to filling in these blanks as far as these MFT parameters. Okay, so putting all of this together, we can run our blocks through the simulator, and we can get our production forecast. So here's an overview of the results. This is the block model, and the colors indicate the flotation recovery. So the reds and the yellows are the high recovery samples, or the high recovery blocks in the deposit. The turquoise and the blue are going to be the lower recovery parts of the ore body. Again, we can summarize this year by year, and we can do our sensitivity analysis, and we can predict the overall performance for the next 20 or so years, or even further into the future, with our confidence levels. And so these are our 95% confidence indicated with the dotted lines. And so, yeah, we're expecting a fairly decent copper recovery. And due to the number of samples, the sensitivity on that is quite good. There's not that much downside risk. Okay, so very briefly into the moly flotation circuit design. As I mentioned before, this has a lot of challenges in generating enough concentrate or enough material to start your moly test work. As an example, if the plant was running, you know, if we had an existing plant and we had 100 kilograms of feed, we'd get, again, around about 1.3 kilograms of concentrate. However, we're not going to get that much material from laboratory test work, and then we needed to do further testing on that. We wanted to do SFR testing that requires at least 20 kilograms of material, and so we had to come up with a way of obtaining this feed to the moly circuit. And then that obviously requires a lot of material, a lot of ore. We also wanted to explore doing variability testing. So could we get a large amount of ore to be processed, and could we get it at different compositions to investigate the variability? And then another thing that comes out of here, and I'll get into it in a bit more detail later on, is that the concentrate produced from the test work was very high grade, almost pure moly, and so we weren't sure that we would be able to get that in the real plant. So to develop or to obtain our flotation concentrate for our moly circuit, we ran pilot plants. We ran pilot plants at SGS Chile, and they were very successfully run. We obtained a lot of concentrate, but to do this, we had to do a lot of planning. As I said, we wanted to investigate variability. So we looked at how many different samples can we run through this pilot plant that are going to be meaningful. And so we looked at things that we expected to influence the process. So for example, the grade of moly that we were expecting. The clay content, we'd found out in this project, clay was quite significant, and was that going to influence the process? And then we, of course, looked at the different ore types that had shown different performance on the copper side. And we thought, well, this is going to influence our moly as well. So let's investigate these different ore types. From the samples that were available, it was a number of, it was a large amount of drill core. We were able to run our flotation simulator on the copper circuit, and we were able to calculate how much concentrate we expected from each of the different composites that we'd put together. And so we could determine whether we had enough material to collect the further downstream material for sampling and testing. I mentioned before, we needed a model of the stage flotation reactor. In the end, we were able to create a circuit model for the stage flotation reactor circuit run in series by manipulating our laboratory flotation test model and putting that into circuit, and then running our benchmarker to try and fit that model. And we seem to do quite well. So over here, we've got the measured results from the test work compared to the simulated results while running our pseudo SFR model. Some of the pyrite values were a little bit out, as you can see here, and it turned out that's more to do with the test work not necessarily being in steady state. But yeah, the model performed well. Another problem, as I mentioned, is having enough material for the downstream test work. The test work, the cleaner test work on the SFR concentrate, the objective of that work was to obtain high-grade concentrate for marketing analysis. And so the objective was not to get high recovery in this cleaner test work. And so for many of the samples, the high grade wasn't possible. Well, the target was to get as high grade as possible. And so this happened with very low concentrate recovery. So we start off with about 25 kilograms feeding our rougher circuit, our SFR circuit. And in the end, on average, we ended up with about 12 grams of final moly con. Enough for some analysis, but not not conducive to how the full circuit would operate. The mass recoveries themselves are shown here. So it's around about 0.04, that's percentage, 0.04%. As far as the moly itself, the overall recovery of moly was about 1.8% over all the tests, when we'd expect around about an 80% recovery. So of course, that final concentrate that we got was very high grade. We didn't expect that. And so we knew that when we were going to recover up to 80% moly, we would have more of the unliberated locked moly particles. And so we looked at our mineralogical analysis, and we modeled the circuit through the mineralogy. So we essentially mass balanced the different mineral groupings in terms of liberations over the entire circuit. So we created these different classes. So we looked at the different liberation classes of moly. We figured out what was associated with it in terms of the other minerals, being copper sulfide, pyrite, and gangue. And we created these different moly particles that we could then run through the simulator. Again, we could fit this in our model with all the mineralogical work. We could mass balance by mineralogy. And you can see it came out pretty well. The mineralogy points are sitting here, not quite on the parity line, but well fitted, and giving good indication of what we expected to happen in the circuit. So we could model the entire open circuit test work campaign by the different moly liberation classes as shown here. Okay, so that is how we developed the moly circuit. Now, what can we do with it? Well, we want to run our full plant simulation, and we want to know what's going to happen on the full scale. So here's the moly circuit that we have. It essentially has 4 stages of cleaning. And we had a calibrated model based on all this test work of how the moly was going to perform in terms of its kinetics entering from the copper circuit. So we could run it through our simulator using that same technique with the optimal grade recovery curves. We could analyze the different samples we would expect. Now, this isn't just the pilot plant samples, but all the samples we would expect based on our copper circuit simulations. And we could aggregate those year by year based on the representation of those samples within each year. So again, that allows us to choose a concentrate grade point. In this case, 48% was the realistic point. There are some years where it's not possible to get a higher grade simply because of the grade of moly in the feed. So putting all of this together, we end up with a production forecast by year. And I've superimposed the moly feed grade on this. So you can see that turns out to be a key driver in the model. Okay, so a lot of technical things in there. You can read through my conclusions there, but essentially we've developed a very comprehensive overall complete flow sheet analysis for this particular circuit, and it allows us to give very accurate predictions of what we expect our production forecast and sensitivity to be. So yeah, thank you very much for your attention.